A residual current device, or residual current circuit breaker, is an electrical wiring device that disconnects a circuit whenever it detects that the electric current is not balanced between the energized conductor and the return neutral conductor. Such an imbalance may indicate current leakage through the body of a person who is grounded and accidentally touching the energized part of the circuit. A lethal shock can result from these conditions. RCCBs are designed to disconnect quickly enough to prevent injury caused by such shocks. They are not intended to provide protection against overcurrent or all short-circuit conditions. In the United States and Canada, a residual current device is most commonly known as a ground fault circuit interrupter, ground fault interrupter, or an appliance leakage current interrupter. Ground fault condition is defined as an unintentional, electrically conducting connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors, metallic enclosures, metallic raceways, metallic equipment, or earth. In the United Kingdom, a residual current device is referred to as an RCD or an RCBO when including overcurrent protection. Non-residual current circuit protection devices are called circuit breakers or MCBs. Infrequently they can be called trips or trip switches. In Australia, they are sometimes known as safety switches or an RCD. A residual current circuit breaker with overload protection combines the functions of overcurrent protection and leakage detection. An earth leakage circuit breaker may be a residual current device, although an older type of voltage-operated earth leakage circuit breaker exists. Residual current device is a generic term covering both RCCBs and RCBOs. Purpose and operation. RCDs are designed to disconnect the circuit if there is a leakage current. By detecting small leakage currents and disconnecting quickly enough, they may prevent electrocution. They are an essential part of the automatic disconnection of supply, that is to switch off when a fault develops, rather than rely on human intervention. This is one of the essential tenets of modern electrical practice. There are also RCDs with intentionally slower responses and lower sensitivities, designed to protect equipment or avoid starting electrical fires, but not disconnect unnecessarily for equipment which has greater leakage currents in normal operation. To prevent electrocution, RCDs should operate within 25 to 40 milliseconds with any leakage currents of greater than 30 milliamperes, before electric shock can drive the heart into ventricular fibrillation, the most common cause of death through electric shock. By contrast, conventional circuit breakers or fuses only break the circuit when the total current is excessive. A small leakage current, such as through a person, can be a very serious fault, but would probably not increase the total current enough for a fuse or circuit breaker to break the circuit, and certainly not to do so fast enough to save a life. RCDs operate by measuring the current balance between two conductors using a differential current transformer. This measures the difference between current flowing through the live conductor and that returning through the neutral conductor. If these do not sum to zero, there is a leakage of current to somewhere else, and the device will open its contacts. It is important to realize that operation does not require a fault current to return via the earth wire in the installation. The trip will operate just as well if the return path is via plumbing, contact with terra firma, or any other current path. Automatic disconnection and a measure of shock protection is therefore still provided even if the earth wiring of the installation is damaged or incomplete. Residual current detection is complementary to overcurrent detection. Residual current detection cannot provide protection for overload or short-circuit currents, except for the special case of a short circuit from live to ground. For an RCD used with three-phase power, all three live conductors and the neutral must pass through the current transformer. Typical features. The diagram depicts the internal mechanism of a residual current device. The device pictured is designed to be wired in line in an appliance power cord. It is rated to carry a maximum current of 13 amperes and is designed to trip on a leakage current of 30 megaamperes. This is an active RCD. That is, it latches electrically and therefore trips on power failure, a useful feature for equipment that could be dangerous on unexpected re-energization. Some early RCDs were entirely electromechanical and relied on finely balanced sprung-over-center mechanisms driven directly from the current transformer. As these are hard to manufacture to the required accuracy, and prone to drift insensitivity both from pivot wear and lubricant dry out, the electronically amplified type with a more robust solenoid part as illustrated are now dominant. The incoming supply and the neutral conductors are connected to the terminals at and the outgoing load conductors are connected to the terminals at. The earth conductor is connected through from supply to load uninterrupted. When the reset button is pressed, the contacts and hidden behind, close, allowing current to pass. The solenoid keeps the contacts closed when the reset button is released. The sense coil is a differential current transformer which surrounds the live and neutral conductors. In normal operation, all the current down the live conductor returns up the neutral conductor. The currents in the two conductors are therefore equal and opposite and cancel each other out. Any fault to earth causes some of the current to take a different return path, which means there is an imbalance in the current in the two conductors, or, more generally, a non-zero sum of currents from among various conductors. This difference causes a current in the sense coil which is picked up by the sense circuitry. The sense circuitry then removes power from the solenoid and the contacts are forced apart by a spring, cutting off the electricity supply to the appliance. The device is designed so that the current is interrupted in milliseconds, greatly reducing the chances of a dangerous electric shock being received. The test button allows the correct operation of the device to be verified by passing a small current through the orange test wire. This simulates a fault by creating an imbalance in the sense coil. If the RCD does not trip when this button is pressed, then the device must be replaced. Form factors: a ground fault circuit interrupter circuit breaker and residual current breaker with overloader devices which combine the functions of a residual current device with a circuit breaker. They detect both supply imbalance and overload current. In Europe, RCDs can fit on the same DIN rail as the MCBs, however the bush bar arrangements in consumer units and distribution boards can make it awkward to use them in this way. If it is desired to protect an individual circuit, an RCBO can be used. This incorporates an RCD and a miniature circuit breaker in one device. Electrical plugs which incorporate an RCD are sometimes installed on appliances which might be considered to pose a particular safety hazard, for example long extension leads which might be used outdoors or garden equipment or hair dryers which may be used near a bath or sink. Occasionally an inline RCD may be used to serve a similar function to one in a plug. By putting the RCD in the extension lead, protection is provided at whatever outlet is used even if the building has old wiring, such as knob and tube, or wiring that does not contain a grounding conductor. In North America, GFI receptacles can be used in cases where there is no grounding conductor, but must be labeled as ungrounded. An ungrounded GFI receptacle will trip using the built-in test button, but will not trip using a GFI test plug, because the plug tests by shorting a small current from line to the non-existent ground. Electrical sockets with included RCDs are becoming common. Combined with overcurrent devices, residual current and overcurrent protection may be combined in one device for installation into the service panel. This device is known as a GFCI breaker in the USA and Canada, and as an RCBO in Europe. In the US, RCBOs are more expensive than RCD outlets. As well as requiring both line and neutral input and output, many GFCI RCBO devices require a functional earth connection. This serves to provide both the community and to reliably operate the device if the input side neutral connection is lost but live and earth remain. For reasons of space, many devices, especially in DIN rail format, use flying leads rather than screw terminals, especially for the neutral input and FE connections. Additionally, because of the small form factor, the output cables of some models are used to form the primary winding of the RCD part, and the outgoing circuit cables must be led through a specially dimensioned terminal tunnel with the current transformer part around it. This can lead to incorrect fail-trip results when testing with meter probes from the screw heads of the terminals, rather than from the final circuit wiring. More than one RCD feeding another is unnecessary, provided they have been wired properly. One exception is the case of a TT earthing system where the earth loop impedance may be high, meaning that a ground fault might not cause sufficient current to trip an ordinary circuit breaker or fuse. In this case a special 100 mA trip current time delayed RCD is installed covering the whole installation, and then more sensitive RCDs should be installed downstream of it for sockets and other circuits which are considered high risk. Testing. RCDs can be tested with built-in test button to confirm functionality on a regular basis. RCDs if wired improperly may not operate correctly and are generally tested by the installer to verify correct operation. Use of a solenoid voltmeter from live to earth provides an external path and can test the wiring to the RCD. Such a test may be performed on installation of the device and at any downstream outlet. Limitations. A residual current circuit breaker cannot remove all risk of electric shock or fire. In particular, an RCD alone will not detect overload conditions, phase-to-neutral short circuits or phase-to-phase short circuits. Overcurrent protection must be provided. Circuit breakers that combine the functions of an RCD with overcurrent protection respond to both types of fault. These are known as RCBOs, and are available in 2, 3 and 4-pole configurations. RCBOs will typically have separate circuits for detecting current imbalance and for overload current but will have a common interrupting mechanism. An RCD will help to protect against electric shock where current flows through a person from a phase to earth. It cannot protect against electric shock where current flows through a person from phase to neutral or phase to phase, for example where a finger touches both live and neutral contacts in a light fitting. A device cannot differentiate between current flow through an intended load from flow through a person, though the RCD may still trip if the person is in contact with the ground as some current will still pass through the person's finger and body to earth. Whole installations on a single RCD, common in older installations in the UK, are prone to nuisance trips that can cause secondary safety problems with loss of lighting and defrosting of food. Frequently the trips are caused by deteriorating insulation on heater elements such as water heaters and cooker elements or rings. Although regarded as a nuisance, the fault is with the deteriorated element and not the RCD. Replacement of the offending element will resolve the problem. Replacing the RCD will not. In the case of RCDs that need a power supply, a dangerous condition can arise if the neutral wire is broken or switched off on the supply side of the RCD, while the corresponding live wire remains uninterrupted. The tripping circuit needs power to work and does not trip when the power supply fails. Connected equipment will not work without a neutral, but the RCD cannot protect people from contact with the energized wire. For this reason circuit breakers must be installed in a way that ensures that the neutral wire cannot be switched off unless the live wire is also switched off at the same time. Where there is a requirement for switching off the neutral wire, 2-pole breakers must be used. To provide some protection with an interrupted neutral, some RCDs and RCBOs are equipped with an auxiliary connection wire that must be connected to the earth push bar of the distribution board. This either enables the device to detect the missing neutral of the supply, causing the device to trip, or provides an alternative supply path for the tripping circuitry, enabling it to continue to function normally in the absence of the supply neutral. Number of poles. RCDs may comprise 2 poles for use on single-phase AC supplies, 3 poles for use on 3-phase AC supplies or 4 poles for use on 3-phase and neutral supplies. Specially designed RCDs can also be used with both AC alternating current and DC direct current power distribution systems. Rated current. The rated current of an RCD is chosen according to the maximum sustained load current it will carry, so generally if the RCD is connected in series with a single fuse or circuit breaker, the rated current of the RCD shall be at least the same as the fuse or circuit breaker, though in the case of an RCD feeding many circuit breakers, an allowance for load diversity may or may not be permissible depending on the type of load expected. Sensitivity. RCD sensitivity is expressed as the rated residual operating current, noted EN. Preferred values have been defined by the IEC, thus making it possible to divide RCDs into 3 groups according to their EN value. High sensitivity, 6 €10 €30 MA. Medium sensitivity, 100 euro 300 euro 500 euro 1000 megaamperes, low sensitivity, 3 euro 10 euro 30 Note that the nominal value of residual current indicated above is not an absolute value. More information is presented below. Type: Standard IEC 60755 defines three types of RCD depending on the characteristics of the fault current. Type AC, RCD for which tripping is ensured, for residual sinusoidal alternating currents. Type A, RCD for which tripping is ensured, as for type AC, for residual pulsating direct currents, for residual pulsating direct currents superimposed by a smooth direct current of 6 mA, with or without phase angle control, independent of the polarity. Type B, RCD for which tripping is ensured, as for type A, for residual sinusoidal currents up to 1 kHz, for residual sinusoidal currents superposed by a pure direct current, for pulsating direct currents superposed by a pure direct current, for residual currents which may result from rectifying circuits, 3-pulse star connection or 6-pulse bridge connection, 2-pulse bridge connection line-to-line with or without phase angle monitoring, independently of the polarity. Break time: there are two groups of devices, G for instantaneous RCDs. Minimum break time, immediate, maximum break time, 200 milliseconds for 1 EN, 150 milliseconds for 2 EN, and 40 milliseconds for 5 EN. S or T for RCDs with a short time delay, minimum break time, 130 milliseconds for 1 EN, 60 milliseconds for 2 EN, and 50 milliseconds for 5 EN, maximum break time, 500 milliseconds for 1 EN, 200 milliseconds for 2 EN, and 150 milliseconds for 5 EN. Surge current resistance: the surge current refers to the P current an RCD is designed to withstand using a test impulse of specified characteristics. The IEC 61008 and IEC 61009 standards impose the use of a 0.5 microseconds/100 kHz damped oscillator wave to test the ability of residual current protection devices to withstand operational discharges with a P current equal to 200 A. With regard to atmospheric discharges, IEC 61008 and 61009 standards establish the 8/20 microsecond surge current test with 3 kA P current but limit the requirement to RCDs classified as selective. History and nomenclature: the World Euro unregistered trademark S first high-sensitivity earth leakage protection system, was a second harmonic magnetic amplifier core balance system, known as the MAGAMP, developed in South Africa by Henri Rubin. Electrical hazards were of great concern in South African gold mines, and Rubin, an engineer at the company FWJ Electrical Industries, initially developed a cold cathode system in 1955 which operated at 525 V and had a tripping sensitivity of 250 megaamperes. Prior to this, core balance earth leakage protection systems operated at sensitivities of about 10 A. The cold cathode system was installed in a number of gold mines and worked reliably. However, Rubin began working on a completely novel system with greatly improved sensitivity, and by early 1956, he had produced a prototype second harmonic magnetic amplifier type core balance system. The prototype MAGAMP was rated at 220 V, 60 A and had an internally adjustable tripping sensitivity of 12.5 euro 17.5 megaamperes. Very rapid tripping times were achieved through a novel design, and this combined with the high sensitivity was well within the safe current time envelope for ventricular fibrillation determined by Charles Dalziel of the University of California, Berkeley, USA, who had estimated electrical shock hazards in humans. This system, with its associated circuit breaker, included overcurrent and short-circuit protection. In addition, the original prototype was able to trip at a lower sensitivity in the presence of an interrupted neutral, thus protecting against an important cause of electrical fire. Following the accidental electrocution of a woman in a domestic accident at the Stilfontein gold mining village near Johannesburg, a few hundred FWJ. 20 MA earth leakage protection units were installed in the homes of the mining village during 1957 and 1958. FWJ Electrical Industries, which later changed its name to FW Electrical Industries, continued to manufacture 20 MA single-phase and three-phase megamp units. At the time that he worked on the megamp, Rubin also considered using transistors in this application, but concluded that the early transistors then available were too unreliable. However, with the advent of improved transistors, the company that he worked for and other companies later produced transistorized versions of earth leakage protection. In 1961, Dalziel, working with Rucker Manufacturing Company, developed a transistorized device for earth leakage protection which became known as a ground fault circuit interrupter, sometimes colloquially shortened to ground fault interrupter. This name for high-sensitivity earth leakage protection is still in common use in the USA. In the early 1970s, most North American GFCI devices were of the circuit breaker type. GFCIs built into the outlet receptacle became commonplace beginning in the 1980s. The circuit breaker type, installed into a distribution panel, suffered from accidental trips mainly caused by poor or inconsistent insulation on the wiring. False trips were frequent when insulation problems were compounded by long circuit lengths. So much current leaked along the length of the conductor's insulation that the breaker might trip with the slightest increase of current imbalance. The migration to outlet receptacle-based protection in North American installations reduced the accidental trips and provided obvious verification that wet areas were under electrical code required protection. European installations continue to use primarily RCDs installed at the distribution board, which provides protection in case of damage to fixed wiring. In Europe, socket-based RCDs are primarily used for retrofitting. Regulation and adoption. Regulations differ widely from country to country. In most countries, not all circuits in a home are protected by RCDs. If a single RCD is installed for an entire electrical installation, any fault may cut all power to the premises. Australia. In Australia, residual current devices have been mandatory on power circuits since 1991 and on light circuits since 2000. Europe. Belgian domestic installations are required to be equipped with a 300 mA residual current device that protects all circuits. Furthermore, at least one 30 mA residual current device is required that protects all circuits in wet rooms as well as circuits that power certain wet appliances. Electrical underfloor heating is required to be protected by a 100 mA RCD. These RCDs must be of type A, Italy. The Italian law prescribes RCDs with no more than 30 mA residual current for all domestic installations to protect all the lines. The law was recently updated to mandate at least two separate RCDs for separate domestic circuits. Magnetic and thermal protection has been compulsory since 1968. Germany requires the use of RCDs with no more than 30 mA on sockets up to 20A which are for general use. This rule was introduced in June 2007. Turkey requires the use of RCDs with no more than 30 mA and 300 mA in all new homes since 2004. This rule was introduced in RG 16200-25494. Norway. In Norway, it has been required in all new homes since 2002, and on all new sockets since 2006. United Kingdom. The previous 16th edition of the IEE electrical wiring regulations required use of RCDs for socket outlets that were liable to be used by outdoor appliances. Normal practice in domestic installations was to use a single RCD to cover all the circuits requiring RCD protection but to have some circuits not RCD protected. This was to avoid a potentially dangerous loss of lighting should the RCD trip. Protection arrangements for other circuits varied. To implement this arrangement, it was common to install a consumer unit incorporating an RCD in what is known as a split-load configuration, where one group of circuit breakers is supplied direct from the main switch and a second group of circuits is supplied via the RCD. This arrangement had the recognized problems that cumulative earth leakage currents from the normal operation of many items of equipment could cause spurious tripping of the RCD, and that tripping of the RCD would disconnect power from all the protected circuits. The current edition of the regulations requires that all socket outlets in most domestic installations have RCD protection, though there are exemptions. Cables buried in walls must also be RCD protected. Refer to 17th edition Amendment 1 effective from January 2012. Provision of RCD protection for circuits present in bathrooms and shower rooms reduces the requirement for supplementary bonding in those locations. 2 RCDs may be used to cover the installation, with upstairs and downstairs lighting and power circuit spread across both RCDs. When one RCD trips, power is maintained to at least one lighting and power circuit. Other arrangements, such as the use of RCBOs, may be employed to meet the regulations. The new requirements for RCDs do not affect most existing installations unless they are rewired, the distribution board is changed, a new circuit is installed, or alterations are made such as additional socket outlets or new cables buried in walls. RCDs used for shock protection must be of the immediate operation type and must have a residual current rating of no greater than 30 mA. If it can be shown that spurious tripping would cause a greater problem than the risk of the electrical accident the RCD is supposed to prevent, RCDs may be omitted, providing affected circuits are clearly labeled and the balance of risks considered. This may include the provision of alternative safety measures. North America. In North America, RCD receptacles invariably have rectangular faces and accept so-called decorator faceplates. GFCI outlets can be mixed with regular outlets or with switches in a multi-gang box with a standard cover plate. Arc fault circuit interrupters are required by current NEC code in locations such as sleeping rooms and incorporate GF protection. As a result, the slightly more expensive GFCI circuit breakers for load centers are less commonly used in residential applications. In Canada and the United States, 2-wire outlets may be replaced with GFCIs to protect against electrocution, and a grounding wire does not need to be supplied to that GFCI. The outlet must be labeled as such. The GFCI manufacturers provide tags for the appropriate installation description. GFCI receptacles can be connected to also protect all the downstream receptacles on that circuit. GFCI devices approved for protection against electric shock trip at 5 mA within 25 ohm. A GFCI device which protects equipment is allowed to trip as high as 30 mA of current. This is known as an equipment protective device. RCDs with trip currents as high as 500 mA are sometimes deployed in environments where a lower threshold would carry an unacceptable risk of accidental trips. These high-current RCDs serve for equipment and fire protection instead of protection against the risks of electrical shocks. GFCI outlets are required by code in most places where an easy path to ground exists, such as wet areas, rooms with uncovered concrete floors and outdoor areas. In the U.S., successive editions of the National Electrical Code required GFCIs for additional areas, underwater swimming pool lights, construction sites, bathrooms and outdoor areas, garages, near hot tubs or spas, hotel bathrooms, kitchen counter receptacles, crawl spaces and unfinished basements, wet bar sinks, and laundry sinks. South America, Brazil, since NBR 5410 residual current devices and grounding are required for new construction or repair in wet areas, outdoor areas, interior outlets used for external appliances, or in areas where water is more probable like bathrooms and kitchens. See also: arc fault circuit interrupter, earth leakage circuit breaker, insulation monitoring device, domestic AC power plugs and sockets. References. External links: GFCI's fact sheet, test of RCCB as per IEC 61008/61009.